In this video, we will be discussing the load line concept, and 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 to do that, we will take an NPN transistor in common emitter configuration. So this is emitter, and this will be collector, and this is the base, right? And let's have some signal, and let's bias. So this is arrow out, so this is NP, this is NPN. So here we will have the positive, negative, and we'll go here in this direction. Then we will keep the load RL, okay, and then we need a VCC, so this has to be reverse biased. So here we'll have positive and negative. So so this will be RL, and here we can have the output, and that output will be ICRL. Okay, so can choose the direction of current, and this is my VCE, and let's assume this is VBB, and this is VCC. Now, what we want is the load line for this circuit, and have some analysis of that. Now, if we make use of Kirchhoff's second law in the output circuit, we will have VCE equal to VCC minus ICRL. Okay, that should be the case. And if I want to have IC from this equation, so ICRL will be it will be VCC then minus VCE. So for IC, I have VCC by RL minus VCE by RL. Now IC will be minus 1 by RL times VCE plus VCC by RL. Now this equation is exactly the equation of a straight line, like y is equal to mx plus c. So here, if we compare this equation with this equation, we have the slope, and that slope will be given by this m. So the slope here we will have is minus 1 by RL. Now, to use some boundary conditions for this problem, now in this given circuit, if we see here, VCC and RL they are constants, and VCE and IC, they are the variables, right? So this VCE is a variable and IC is the variable. Now 2 points can be easily calculated from this equation. We can calculate the 2 points using this equation that's written down here. So if I say that say for example, the case 1, in the first case, for IC, if I choose IC equal to 0, what's going to be the output is we will have VCE equal to VCC, and for VCE equal to 0, we will have IC equal to VCC by RL. Okay, so these will be the outcomes of the conditions that we have imposed. IC equal to 0 and VCE comes out to be VCC. VC equal to 0, then IC comes out to be VCC by RL. Now these points are if we go to the characteristics of the original configuration of transistor in common emitter mode, how does it look like? It's we have y-axis, we have x-axis. This is VCE, and this is IC. Yeah, this is IC, and then we have what we have is we have the output characteristics like this, and like this. Okay, so let me choose a dotted line for IB equal to 0. So this is IB equal to 0, and let me choose the loss curve for IB equal to IB. Okay, that should be the case. So now we have 2 points. Now for IC equal to 0, so we are on the x-axis. In that case, VCE equals VCC. So for that we have a point here, and that is VCE equal to VCC. And then we have for VCE equal to 0, then that means we are on y-axis, and we have a point here that IC equals to VCC by RL. Now, if we join these two points, we have a load line. We have a DC load line. So what would I like to do here is that I will mark this point as A, and I will mark this point as B. So these points A and B, they represent the collector characteristics. I mean, the line joining these 2 points is my static or DC load line. Thus the load line is basically the locus. It is the locus of only pairs of values for IC and VCE, and which can exist for the given values for VCC and RL, right? So it is important to note at this point, and what's important is that the load line depends only on VCC and RL, and is totally independent of transistor characteristics. So this line, the slope of this line, if we go back to that equation, I mean, here is that the slope is -1 by RL. It's -1 by RL, which we have already discussed. So this slope of the line depends on the load resistance only, and is -1 by RL. So that is -1 by RL. So we can see that. So the intersection of this DC load line with the base current base current or the point that we will obtain is called as operating point, or we call that as quiescent point of transistor, right? Now I should say that this load line is the locus of all set of IB, we have IC and VCE, right? That can exist for a particular transistor with certain values of this VCC and RL, right? So So we have a load line, and we have a Q point. Now the question is that suppose the point that where this DC load line this DC load line intersects such that IB is equal to 0. Uh, Now this curve that we have here is the cutoff point, right? This point on this curve. So at this point, base current is 0. It's clear, and the collector current is negligibly small. As the normal transistor action is lost at this point, so we say that this is at this point this VCE, it's cut off. It's cut off at VCC, right? And the point where we have this load line intersects with IB, this IB. Okay, so this point will refer to the point of saturation, right? Now at this point the collector current is maximum. At this point this collector current is maximum. To a close approximation, we can think of this IC saturation. This IC saturation is VCC by RL. So all operating points between cutoff and saturation region are active regions of transistor. These are active regions of transistor, and certainly there has to have a state where we are interested in stabilizing this Q point where this transistor has to be operated. Now, talking about, I mean, every amplifier, if I have here, we talked about the DC load line. If we talk about the AC load line for the same case, every amplifier it will see basically the AC load line along with DC load line, right? The AC load line may be found by equivalent impedance of the circuit components in the emitter to collector, in the emitter to collector. So we have always a load line associated with this load line, and what's referred as the AC load line. And in that case, we have a situation where we look for, say, for example, if I have to mark the AC load line here, say it's like this. Now, what's going to happen is that if instead of RL we have RL dash, if this RL dash is the equivalent impedance, that's the equivalent impedance of the circuit components involved in the common emitter configuration. Then the slope of the AC load line that we generalize here will be minus 1 by RL dash. So for AC load line, we will have minus 1 by RL dash. Okay, as AC load lines must pass through the quiescent point. So wherever is a comfortable quiescent point, this AC line should pass through this Q point, because the collector current under static conditions must remain unchanged. It's very important for the collector current. There is a variation to remain static, to remain constant. So thus AC load lines are not established by the intersection of accesses that we use for the DC line here. So these are also called the dynamic load lines. So that they keep on changing and may also be defined as the locus of all corresponding values of instantaneous collector current and voltage during the cycle of the signal that's going to be operated on this load line. So this is my AC load line. For the sake of understanding, they can have a range of AC load lines, uh, and this is my my DC load line for the transistor in common emitter configuration.